This is a lesson on balancing equations. Again, this is another review. You should not have too much difficulty with this. The meaning of a balanced equation. You write balanced equations to show the conservation of matter. Atoms cannot be created nor destroyed in a chemical process, so the number of atoms on the left have to be the same as the number of atoms on the right. If you have 4 irons on the left, you have 4 irons on the right, so etc., etc., etc. The coefficients can stand for, let's see the old 2H, O2 yields, the arrows red yields, H2O. The coefficients could stand for the number of atoms or molecules, could stand for the number of moles of the particles, or a ratio of 2 to 1 to 2. So individual particles, moles of particles, or that. Above the arrow, sometimes you can write in special conditions, electricity, certain pressures, things like that. Usually we don't see that. Or spark or something like that. Conditions, atmosphere, things like that. The other thing that you might have is symbols for a state. The symbols on the end, and they're very obvious symbols. S for solid, L for liquid. I do the cursive L, so it looks like an L. And G for gas, and AQ standing for an aqueous solution dissolved in water. They follow behind. So water, let's call that a liquid. Oxygen is a gas, and hydrogen is a gas. If you have to put in the symbols, put them at the very end. It just clogs up and makes it more difficult to try to figure out what you got to balance. I've seen people try to balance the number of G's and L's on either side. Please don't do that. So, for example, of balancing the equation, titanium 4 chloride plus water forms titanium oxide, titanium 4 oxide, plus hydrochloric acid, or hydrogen chloride. HCl, if it's aqueous, that would be a hydrochloric acid. If it's a gas, then it's hydrogen chloride. There is a difference. I leave enough spaces so that you can put in numbers, and if you were to put in the phases afterwards, I would leave spaces there. Like that would be bigger for that. I look for the one that is in the biggest discrepancy. So there's 4 CLs over here, there's 1 CL over here. So I would balance the biggest difference first and put a 4 in front of each CL. Now you got 4 H's, you got 2 H's, so you got to multiply by 2. 2 times 2 is 4. And you have 2 O's and 2 O's and 1 TI and 1 TI. And you can go back and balance things, check them out again if you wish, just to make sure that everything's balanced. Sometimes you don't trust yourself. Iron 2 sulfide plus oxygen yields iron 3 oxide. And sulfur dioxide. On these, if you have a single element, balance that single element last. Things tend to work out better for you that way. There's the thing that's out of whack the most is the iron, so there's 2, so you need a 2 there. Now you have 2 S's, you gotta put a 2 there. And now you count up the number of oxygens on this side. The irons are balanced, sulfurs are balanced, again leaving the oxygen for last. You have 3 plus 4 is 7, but they only come in pairs. Oops. Well, what you do is you put that 7 that you need and double everything else out. You write down like 7 halves, and then to get rid of the fraction 2, you multiply by the common denominator, which is 2. So 7, take that out 4, 2, take that out 4. So that's the standard way. Works great with combustion, which is what we talked about in the last thing, where you have a hydrocarbon burning itself, in other situations like that. Pretty much that's the entire lesson, and that ends this lesson. Okay, this is a unit on stoichiometry. On stoichiometry, the first step is always to have a balanced equation. They may or may not give it to you. They can give it to you in words. They can give it to you in, like, nitrogen plus hydrogen reacts to form ammonia. They can give it to you in an unbalanced form. Or they can give it to you as a balanced form. So either way, you've got to balance the equation. Simplest type is if you're going from moles to moles. If you have 5 moles of nitrogen gas, how many moles of hydrogen gas will be produced? So you write down what you know. 5 moles of nitrogen. And you need to eliminate nitrogen, so N2 goes on the bottom. You're trying to find hydrogen, so that H2 goes on top. 3H2 and 1N2 is the ratio, and you get that from the balanced equation. And then you eliminate the N2s, and you're left with 15 moles of hydrogen gas. Sometimes you can start with moles and go to grams, or start with grams and go to moles. In that case, it's a 2-step problem. Moles and moles is a 1-step. If you have 5 moles of nitrogen gas, how many grams of hydrogen gas will be produced? Well, you start off with 5 moles of N2, and you need to change that to moles of hydrogen, so that's the same thing as above. But that gives you moles of hydrogen. They specifically ask for grams of hydrogen. So now you need to multiply 2 grams of hydrogen is 1 mole. Now the moles cancel out, and you're left with 30 grams of hydrogen gas. The typical thing that you would do is grams to grams. That's the most common one. 7.5 grams of hydrogen gas will make how many grams of ammonia gas? In this case, it's a 3-step problem. 7.5 grams of hydrogen. First thing is you got to change grams to moles. 1 mole is 2 grams of hydrogen. Now you have moles of hydrogen, so now you need to change moles of hydrogen to moles of ammonia. Ammonia is 2. That's coming from the coefficient of the equation, and 3H2. Now you have moles of ammonia, but you need to change that to grams. 17 grams is 1 mole. 17 grams coming from 14 plus 3 on the ammonia side. Do the math, come up with 42.5 grams of ammonia. So that's a typical problem. You might also be given a limiting reactant problem where you have 7.5 grams of hydrogen and 35.0 grams of nitrogen. So this would be a limiting reactant problem. And you change that to grams. If you have a choice, you gotta change to the same thing. You could go straight to moles if they just want to know how many, what's going to run out first, or limiting reactant, sometimes called a limiting reagent. But if you go to grams all the time, it's kind of set piece and it's pretty easy to do. So I said 35, it should be 33. So 33 grams of nitrogen. And as I said before, these are 3-step problems. And on top, if you're going to convert to the same thing, the top is going to be the same. So it's going to be 1 mole, 2 NH3, 17 grams. On limiting reactants, you always have to convert it to the same thing. Otherwise, you don't know what you're missing or what you've got to. 1 mole of nitrogen gas is 28 grams. 1 N2 is coefficient, and 1 mole is on the bottom. You do the math, and you get 40.1 grams of ammonia. You notice that even though you started off with more nitrogen, 33 grams, you ended up with less of this. So the limiting reactant is N2. The limiting reactant. How much ammonia could be produced? 40.1 grams of ammonia. Low score wins. What this means is you can also figure out how much excess hydrogen gas you have by doing this. What you do is you subtract the 42.5 minus 40.1 and you get 2.4 grams of ammonia that could have been produced if all the hydrogen reacted. And you work backwards. You start here, 42.5, and you go the opposite direction, flipping everything around. So it's not really too tough of a problem, because everything that is on the top goes on the bottom, everything on the bottom goes on the top. 1 mole of ammonia is 17 grams, which you got from here. 3H2 and 2 NH3, which is this fraction reversed, and 2 grams and 1 mole on the bottom. Do the math, and you get 0.4 grams of hydrogen gas in excess. That means you have that much. That means you have, like it's about to be dangerous, excess. That means you have that many grams of hydrogen gas still unreacted after everything's all done. The last stuff is percent yield. If they tell you that you actually, in the above problem, limiting reactant problem right here, if you actually produced 36.4 grams of ammonia, what is the percent yield? Well, you produce that divided by 40.1 grams of ammonia, which is how much you really theoretically could have done. So it's the actual divided by theoretical times 100. Do the math, and you get 90.8% yield. So you made 90.8% of what you can do. There's reasons for that. Contamination, side reactions, leakage, lots of reasons that would give you less than that yield. That ends this part on stoichiometry.